Hey, hello there. So this week I'm practicing bit manipulations, and yesterday I went over sort of like a review on the bitwise operations. What are they? What they mean? What they does, and how to use them. Also with some sample usage patterns that I can think of. So for the rest of this week, I'm primarily just gonna try to put those into you practice. So tonight I have two big counting questions. The first one is 191, number of 1 bits. Given a unsigned integer, we should return the number of 1 bits in it. The reason for it to be unsigned is that we want to count the leftmost bit. If it's 1, it's not a negative sign, it's an actual 1 bit in there. So that's why it's an unsigned integer, I guess. So the number example, we have a number with 3 bits, we should return 3. The number with 1 bit, return 1. A number with 31 bits, obviously we return 31. We could the most straightforward brute force kind of a solution is to check position by position. So if this number has 32 positions, we can just do a for loop from 0 to 31 to check the 0's position, 1's position, 3's position, 4's position from the right, whether that position has a 1 bit, and just count all the 1 bit up. The way we can do that, there are multiple ways we can do that. We can shift a 1 bit mask all the way through from the rightmost towards the leftmost, or we can do what I put as here. We can shift the number towards right by the given position and to do an AND operation with a single 1 bit. If this returns a 1, that means that the position at the given position for this number x has a 1 bit in there. So we just throw this check bit into a for loop from 0 to 31 and just count up how many times this will return a 1. So that will give us the required answer. So the time complexity is actually fixed to be 32. Every number we have to run this loop for 32 iterations. And that's definitely a waste for the numbers like this one. They only have 3 bits. So ideally we would want to only do work when necessary. So the way to do that is to utilize another property here. If we do AND between the number and the number subtracted by 1, it's effectively equivalent to clear the very last bit. So in the first example, it only has 3 bits. If we clear the first bit in the rightmost bit in the first iteration, it becomes 0, 0, 0, 0, 0, a bunch of 0, 1, 0, 1, 0. The second iteration, it will become a bunch of 0, 1, 0, 0, 0. And in the third iteration, it will become 0 all the way. So after 3 iterations of clearing the last bit, we can make the number into a 0, and since we do 3 iterations to get to this final result, we know that there are 3 1 bits in this number. So in the worst case, it's still 32, but on average it's much better. It is much better. So let's code this one up instead. So just gonna put a little comment here about how to actually do the clear last bit. Copy and paste. Yeah, the reason is that when you do a subtract by 1, it's making the very last 1 bit to be 0 and add a bunch of 1 towards the right. When you do AND, you will effectively just destroy that very last 1 bit. So what we're going to have is to initialize a counter to count the number of bits. It's 0 in the beginning. And while this number hasn't been reduced to 0 all the way, then we do this removal of the last bit. In the same time, we increment the counter. In the end, we should return this count for a number of bits. So that's the okay. This should be n. Alright, so this is the solution for this question, 191, number of 1 bits. It's The brute force is okay, I guess. It's a 32. It's still constant, but this trick to clear the last bit is going to be much better on average. So the second question is 338. It's called counting bits. So we have a number here, and we actually want to do this bit counting from 0 to that number, so inclusive. So 191 is count one number, this one is count a whole bunch of number in this range. And if we apply this code Hamming weight to all the numbers there, it will be n multiplied by the you know, if we do this bit counting by number, it will be order of a number multiplied by the 32 or something like that. The average time you will need to conduct this clear bits. It's roughly linear to the size of the number, I guess, maybe half. But that's not what this question is really asking. This question is asking for a linear time algorithm. When you think about n numbers and the time has to be linear, true linear, it means that for every number we should do only one operation. How we can do that? I think the important thing to notice is that this number has a range, and when you look at something like number 1, so just enumerate first a few numbers in this range, 0 to a number. We have 0, 1, so just pad this with 0 to show its binary form. We got 1, 0 and 1, 1, 1, 0, 0. So if we know the number of 1 bits for 0, 0, 0, and we know that we can, if we remove the rightmost 1 bit for 0, 0, 1, we get to 0, 0, 0. So the number of 1 bits for 0, 0, 0, 0, 0, 1 is going to be the number of bits in this number plus 1. And for this number, 0, 1, 0, it's the same as 0, 0, 1. It's going to be the number for 1 bits in 0, 0, 0 plus 1. For this one, it will be, for this number, it will be the number of 1 bits in 0, 1, 0 plus 1, because if we clear the very last 1 bit in 3, it becomes 2. So there is a recursive relationship here. Number of bits of this number I, it's going to be the number of bits for if we clear the very last 1 bit, and just add that back into the count. So yeah, so we get to this number by remove the very last 1 bit. So if we know how many bits this number has, just by adding that back, removed 1, we can get to the number of bits for this integer I. And you see that just based on this, if our initial case covers 0, 0, 0, then all the case should be able to fall back to that base case. So the base case is 0 for this. The base case is 0, and we're just going to apply this recursive relationship to build up this required array. So that's pretty much the solution. It's still using this. Still using this clear the last bit trick that I've been using for the previous question, except that it's not really reusing this Hamming weight for the total n times. That's going to be less optimal compared to utilizing this relationship to form a recursive relationship. So yeah, so just gonna code this up really quickly. we're gonna have a vector of integer, which is gonna be the bit count. Let's just call it bit count. And it has a size of this number plus 1 because it's a 0 to that number inclusive. So we're just gonna do a for loop starting from 1, and this has to be less than or equal to, so because it's inclusive. For each iteration, we're gonna increment this I, and the stuff we do inside this for loop, it's basically just populating this new value by using this recursive relationship. So it's literally just copy and paste the formula into the code. And yeah, in the end we should just return this. It should be the solution. So let's try this. It's working and really fast. So this is a true linear time algorithm, because for every new number we just do a lookup and doing a addition, single operation addition, and it's much better than write a function for this and in each iteration in this for loop by calling that to count the bit. It will be much slower compared to this. So but to derive this recursive relationship, we need to utilize this property when we do the clear the bit. So yeah, so that's the bit counting question for today. Tomorrow I'm gonna actually look into the Hamming. I think I'm gonna try to look into the Hamming distance questions. That's also a classic bit manipulation question. So yeah, that's the video for today.